Okay, what we want to do, we want to start talking about how we can, we practice this weird concept of anti-differentiation, just reverse the derivative process we're so familiar with, not that big a deal. You know, we'll get back to that stuff later. We're going to look at something that is seemingly unrelated, and then magically, at some point here in our near future, the two are going to come together and end up being the same thing. Okay, we want to look at the seemingly unrelated topic of adding up areas under curves. Okay, so what I'd like to do today is I want to look at how could we'll start off by looking at how could we estimate the area under the curve 4 minus x squared between 0 and 2. So that's the area that we're going to try to estimate. Now at first, because that's a curve, we can't use some geometric formula. Now if those were triangles or trapezoids or any kind of polygon, we could, with straight sides, we could add that up. That would be a pre-calculus, non-calculus issue, but this is calculus. If we want to be able to get to a point where we can add up the areas under curves, all that stuff goes away, and none of those techniques are going to work. We're going to come up with something different. Well, we're going to start off, we're going to start easy. We're going to start by just trying to make an approximation. Okay, if we want to approximate the area, we'll approximate this curvy area with areas of geometric things that aren't curvy, like rectangles. Rectangles are convenient because they're so easy to get areas from. So what if we were to split this thing up into approximated by 4 rectangles? Okay, so we could use 2 rectangles. If I do 2 rectangles, I have 2 choices. I could either choose these 2 rectangles, I could use those 2 rectangles. Now those are the rectangles, if I had to describe those, I would say that those are circumscribed rectangles because they're outside of the actual area. They're bigger than the actual area. In other words, if I were to define my rectangles, if this is 1 and that's 2, if I defined these rectangles as having widths of 1, and let's say that they're flexible, calculus rectangles, they could start off being really tall, and I'm just going to push them down until they bump into the function.
Why didn't we just use 1 rectangle?
Well, we could. We could also just use 1 rectangle. If I just use
2 then?
If I just use 1 rectangle, it's going to look like this. It would be the green one. If I'm using circumscribed rectangles, it would look like that.
Why are you using 2?
Why would I use 2? You answer that question for me. It's a little bit more precise, isn't it?
So why don't we just use like infinite?
Yeah, why don't you use like 10 or 20 of them?
Why don't you just use 1 for every x coordinate?
For every x coordinate.
Why don't we just...
Okay, these are good white onlys, and in fact, that's our goal, is somehow we can't add up an infinite number of rectangles because it would take infinitely long to do. And we're going to do this manually today, and I don't feel like being here forever, for eternity. So we'll limit ourselves down to a finite number of them. But we're going to be looking for tricks. We're looking for tricks that might allow us to extrapolate this process into maybe a limit, where we could take a limit of what our answer would be if the number of rectangles got really big. In fact, what if it approached infinity? Okay, now that takes some doing to get there, though. That's where we're going with this. You already kind of see the trick, maybe. The more rectangles we have, the better this approximates the curve, right? Everybody agree with that? There's 1. The green rectangle is 1. There's what we have with 2. It's a little better. And if I cut it up even more, I could more closely mirror the edge of that function. Where this comes from, this is called the method of exhaustion. And probably in more ways than one you're going to think after a while. But it's called the method of exhaustion because we're trying to exhaust the extra area under the curve by getting more rectangles. The more rectangles I get, the less of this extra erroneous area I have. I exhaust that. I push it out. So, and this was originally done, by the way, with circles. The way that this was, what inspired Newton and Leibniz to do this was the problem of trying to add up the area of a circle. Okay, that's where this came from. Trying to take, how would we do that? Well, the way they did it was we just took polygons with an increasing number of sides, and as you increase the number of sides of the polygon, the regular polygon, it starts to look more and more circular, and you could find a limiting process there. You approach a certain value, which is, of course, the answer. So that's where it came from originally, but we don't do that very much anymore because we have a formula for that. That's now geometry, but this isn't. This is calculus. Okay, well, let's be a little more precise than this. Let's cut it into 4 pieces instead of 2. Okay, so that's going to look like that. There's
we do 6
now
pieces.
there's 2. We could do 6. We could, and pretty soon we're going to be able to. We'll eventually, not today, but in the near future, we'll come up with a formula for stuff like this that will allow us to choose any number of pieces that we want, called the number of pieces n. And we'll be able to set n to be whatever we want it to be. Okay, but for today, though, let's start with one that's very concrete. Let's just look at how we would add this up for circumscribed rectangles, for uniformly spaced, uniform width, circumscribed rectangles, and for inscribed rectangles.
Bye.
Okay, question?
Oh,
Yeah.
why don't we just use triangles?
Why don't we use triangles?
Yeah, because look, you can put triangles.
You could put triangles in here, you mean?
Yeah.
Well, okay, now, Yen-Yen's actually onto something pretty good there. Why don't we use, I don't think you meant triangles, I think you meant trapezoids.
Yeah, you meant trapezoid.
No, he meant triangles. He was
Trapezoids, and I'll bring this up briefly, and then we're gonna hold off on the what ifs for now. But trapezoids would work the best. Let's take this middle one. What if instead of this red rectangle, I made a green trapezoid
Where's it right?
that did that? Well, it almost matches the surface, doesn't it? Pretty close. Right, this one up here is going to be just a little bit off, but the trapezoids match pretty well, right? Very good question. Why wouldn't we use trapezoids? Because trapezoids match so much better than rectangles. Well, we could. We very well could.
Don't do it better.
What might be our inspiration for using rectangles?
easier.
It's easier. Yeah, it's easier to do. When we have to add up trapezoids, the area of a trapezoid is harder to do than the area of a rectangle. And if we're going to do what we already sort of explained as being our strategy, take a whole bunch of these things and add them up, we'd like to pick the easiest possible kind of shape to add. So rectangles are the easiest, just length times width, right? So that's why we're using rectangles, but trapezoids would work better. And in fact, we're going to come back after we learn how to do all this stuff. What we're going to find is that there are certain kinds of shapes that our trick we're going to develop doesn't apply to. It simply won't work. They're not integrable. And so for those problems where we can't do the calculus, it eludes us for whatever reason. These are just functions that are weird and tricky, and they don't calculus. This type of calculus just won't work for them. Then we have to do an approximation. We don't have a choice. We can't get an exact answer with our trick. And then we will use trapezoids. It's called the trapezoidal rule. And it's a good way to make a quick, accurate approximation of the area under a curve. But it is an approximation. It is not exact. Okay, but we're working towards a solution where we'll get exact answers for now. Okay, so let's compare these two cases now. If we're trying to estimate the area under the curve 4 minus x squared from 0 to 2. We're going to cut these into uniformly wide rectangles. What's going to be the width? 1/2. How'd you get that?
Because 2 rectangles equals 1.
Okay, because 2 rectangles is in one. Okay, good. I see what you're saying. Another way of saying that would be the width of the interval divided by the number of rectangles gives us the width of an individual rectangle.
Right.
Right?
Yeah.
So in this case, 2 divided by 4 rectangles, 2 over 4 is 1/2. That's going to be important to us. We're going to call that delta x. That's going to be the width of our rectangles here shortly, and that's going to be our formula for finding it. The width of the interval divided by the number of rectangles. But we'll get there shortly. Okay, so these circumscribed ones, the ones we push down from above. Now, this function on our interval, isn't this function, we would call it monotonically decreasing in math, or monotone decreasing, meaning it's boring. It's just decreasing the whole time. For a decreasing function, if I'm pushing these rectangles down from on top, where are the rectangles going to bump into the function every time? Which corner?
The far.
Okay, left corner, the upper left corner is where they're always going to bump into the function, right? So we could say then that the height of each rectangle is determined by the value of the function at the left edge of the rectangle. Okay? Now, in calculus, I'm just going to keep throwing in some terminology, not that I expect you to remember it, but if you hear it in context, it's easier to familiarize yourself with it. So, we would say that this is the interval where we're adding up area. Each one of these rectangles defines a subinterval. Okay? So we're going to add up all the subintervals, make up the big interval, right? So the left edge of each subinterval is going to be what determines the height of the rectangle. The width we already know. The width is 1/2 every time. So all we've got to do is just add these things up. The value of the function at x equals 0, because wouldn't that be the left edge of the first rectangle? First one goes from 0 to 1/2. If I put 0 into my function up here, I just get f of 0 is 4 minus 0 squared. 4, duh, right? So the height of this one is 4. Duh. Okay, so this is 4. And the width is 1/2. So what's the area? 2. So there's the area of the first guy. Now what about the second one? Well, the width is 1/2. What about the height? The left edge,
3.75.
about 3.75. What do you know? Yeah. The left edge of the second subinterval, the second rectangle, is going to be at 0.5. If I put 0.5 into my function, 4 minus 0.5 squared is 4 minus 0.125, so I get 3.75, right? Or 0.25, sorry. 3.75. So 3.75 times 1/2 is going to give us, what is that? 1.875. Okay, so there's the area of the second rectangle.
I can hardly see
Okay, that's bad color, isn't it?
it.
It is.
But it's okay, I know what it says it is.
Let me pick it
Really
up.
like thing.
Oh, I can white. There we go. What did I say it was? 1.875. Okay, what about this guy? Okay, this guy is 1/2 by, at x equals 1, the height is 3, right? So it's 1.5, etc. You see where we're going with this? If we add all those up, I'm going to get a sum of all those areas, and the sum is 6.25 if I add them all up. Okay? So 2,
Wait, can you repeat that?
whoops,
I think it was 1.875.
Yeah.
We go over that.
1.875 because I just multiplied, because the width was 0.5
Yeah.
and the height was 3.75.
Oh, you just multiply.
Just multiply.
Not the one that was on my side.
Okay? Yep.
Oh, from down.
If I add all these areas up, 2 plus 1.875, this one's 3 high by 1/2 wide, so it's 0.5. And then this one is going to have a height of 1.75, okay, because that's f of
Right.
1.5 times 0.5 is what? 0.875.
How come all the widths were actually?
Okay, if I add all those up, I get an overall area of 6.25. Okay, if I add all those up. Agreed? Too big though, right? Okay, now I want you to notice something here though. Here's something important coming. Okay, let's look at this guy. Now, what do you notice if I add up these areas of the inscribed rectangles? We're going to see a really important relationship here that later on is going to be big. The first one has a height of, now it's going to be the right edge, isn't it? Because if I inflate these things from the bottom, they bump into the curve at the right edge of each subinterval, each rectangle. Now, wouldn't you agree that the right edge of the first rectangle is equivalent to the left edge of the second?
Yeah.
Ah, how about that? So these heights are going to correspond to those, aren't they? First one's going to have 3.75 times 0.5, which is our 1.875. Second one is going to be this guy, isn't it? And the third one is going to be that guy. Yeah. What about the last one?
0.
It's 0 because it's already bumping into the function, right? So if I add all those up, I get an overall value of 4.25. So what can you tell me about the actual area there? Well, not necessarily, but it's between the two, right? And it would be close to the average. Yeah. Be close to 5.25. It's not, but it's close. Okay? Make sense? All right, so now, how could we get better with this? How could we add these things up? Well, let's maybe make an intermediate step. How could we add up large numbers of these things manually, though, still not using our trick? What if we wanted to? What if we want to break this into, say, 50 rectangles? That's too many to add up manually. If we only have 4, it's probably easiest to do what we just did. Just add them up, using really simple arithmetic and geometry. But if we have a whole bunch of them, we need some tricks. Okay, we need some tricks. We need to come up with some kind of a formula. Now, how could we do that?
Tell me, Doctor.
All right, so let's try this again.
You're so wasteful.
Yes, my
Killing
virtual.
trees.
Okay, I'm gonna kind of stretch this out, so it's gonna be a little bit distorted, so we can just see this a little better. Okay, I want to break this up into a whole bunch of pieces this time, right? Let's start off with our first one, and we'll just do. How about if we do inscribed? It'd be easier.
Way small,
We'll do inscribed rectangles this time.
What do you do?
And I don't want to draw them all, so that just means et cetera, et cetera. And
Because you're lazy.
exactly. And there's our trim, right? Now let's focus on this middle one here. Okay. Well, we need to know, if I want to be able to add up the area of the middle of any of the middle ones, I need to know which rectangle it is, where's the left edge, where's the right edge, etc. Right? Okay. Let's call this the ith subinterval. Okay. So this is going to be number I, meaning I'm going to start at 1, 2, 3, 4, and then I is just some random number between, let's say, the first and the whatever we choose the last one to be. Could be the 8th, could be the 10th. How about if we call it the nth? Okay. This is starting to sound an awful lot like summation stuff that we did last year, isn't it? Little bit, right? Like summation stuff. Right? Okay, so then wouldn't you agree that the area of this ith rectangle is going to be the width of this guy? Okay, now let's call that delta x, because we're going to cut them all the same. We don't know what that's going to be yet, but we ought to be able to figure that out. And then the height is going to be determined by the right-hand edge. Now, if I look at these steps I've taken, I started at 0. In the steps I'm taking, I'm going delta x, so that's 1 delta x. After another step, I'm out 2 delta x, 3 delta x, 4 delta x. Where am I going to be when I get to the right edge of this guy? I delta x. Everybody agree?
Yeah.
Okay. So this point right here is going to be I times delta x, right? That's how many steps I've taken. Okay. So then the height of the function here, if our function is that, what's the height of the function going to be if the x value here is I times delta x? In other words, I've got a point with coordinates I delta x. What's going to go there? It doesn't matter what the x value is. This is telling me what the formula is if I put it in there. I'm plugging in an x value of I times delta x, right? So it's just going to be f of I delta x, right? Now, what is that? If I put, let's find it. What is f of I delta x? Well, that's 4 minus the quantity I delta x squared, right?
Why do we have lots of delta?
Yeah, right. What?
Why do we have to have the
Say it again.
Why do we have to have the delta?
Why do we have to have the delta x?
Yeah, because it's not changing. It's the same.
No, you're right. Okay, the reason we call it delta x is because it's the difference between the left and the right x values. So if I wanted to, here's what I could say. I could say that if this is x sub 0, which is just 0, I could call that x sub 1, that x sub 2, that x sub 3, all the way up to x sub n, whatever the number of rectangles I'm choosing is, right? Then delta x is just going to be the width of this whole interval, right, divided by the number of rectangles. In this case, the width of the whole interval is 2, right? We're going from x equals 0 out here to x equals 2 is where this function crosses the x-axis. So this is actually a value of 2. So what's my delta x going to be then? If I have n rectangles, how wide is each one? 2 over n, right? I've got the whole thing, the whole width divided n times makes each of those 2 over n, right? Well, what if there were 10 rectangles? Then it would just be 2 divided by 10 would be 2/10 or 1/5. Each one would be 1/5 wide, right? Okay, so then we can say that in our case right here, delta x is just going to be 2 divided by the number of rectangles. We can be whatever we want. We haven't pinned that down yet, which is kind of nice. We could, we can see what we get for different answers, different values of n when we're all done. So we got to get this area though. Now, do you see what we're doing with this? If I could add up the area of some random rectangle in there, the ith one, then couldn't I just sum those all up? Couldn't I add those all up as I goes from being the first rectangle to the last one? Right? That's pretty tricky. That's kind of a sort of a close to calculus step right there. That's pre-calculus, but it's a calculus idea. If we can define a generic rectangle in terms of some index variable, as we called it last year, in terms of I, then I should be able to add that quantity up however many times I need to, right? Well, we know that the height is f of I delta x and the width is I delta x, so we got everything we need. The area of the ith rectangle, let's call it a sub I, is just length, or just width times height, right? Or height times width. So that is, there's the height, right? So 4 minus I squared delta x squared times the width, which was just delta x, right? Height times width, everybody agree? And I've been talking a lot, so it's easy to lose track of what I was saying earlier, but here's how we got that height. All we did was we just evaluated our function at that x value, which is I steps of width delta x from our starting place. Okay, so I delta x. But look at this. Delta x is 2 over n. So we could even plug that in down here, right? And this becomes 4 minus I squared times 2 over n squared, because that's our delta x, right? How about that? And then delta x is 2 over n. Now that's pretty cool. Now we've got the area. Look at that. We got the area of this ith rectangle. What's the only unknown in that whole thing? Well, n, I guess, right?
How many rectangles are
Yeah, well, n's the nut, right. That's we have to determine that, but we can set that and say it's going to be 100. Once I set what the number of rectangles is, then look at that. The area of the ith rectangle only depends on I,
How wide?
right? How about that? So I should be able to add those up. Okay. Let's add those up then. Wouldn't you agree that the total area then is just going to equal the sum of, that's a terrible 6. I can't.
That is terrible. That wasn't good.
Yeah, it's a little better.
Wow.
We're going to add up all of the I area, the areas of the I rectangles. Each one is just going to be a sub I, but as I incrementally steps along, that represents one rectangle to the next. The first rectangle it represents is a sub 1. Well, that's, I can point to it. That's a sub 1 right there, right? That area is a sub 1. A sub 2 would be the area of the next one, so on and so forth, and the last one would be a sub n, right? So we should be able to add those all up as I goes from 1 up to, what's our upper limit?
70.
Might be. We haven't said it yet.
I really don't know.
What do we call it for now? N.
And
Okay? That's it, right? Okay? So we're just adding all this stuff up right here for that value of a sub I. That's the area that we developed. Okay, so let's combine that stuff. So we've got our total area equals the sum of this, 4 minus I squared times 2 over n squared times 2 over n as I goes from 1 to n. Okay? Now we can do this really quickly on our calculators. We can sum this up very, very easily and quickly if we know what the value of n is. Let's set a value of n.
100.
And okay, we can do 100. That's fine.
That's right.
Go back to stern.
What's up, Brandon?
It's kind of ziggy and zaggy, isn't it?
Hey, is it really up, Brandon?
No, it's greater digit.
Because spelling.
So if n is 100, okay, if n is 100, we can plug that in everywhere, right? And this becomes the sum from 1 to 100 of 4 minus I squared. What's 2 over n then? If n's 100, so 1 over 50, yeah, times 1 over 50 squared, right?
That's what it is.
Why 50?
Why can't it, does it say that I is, why is it always write shit I in the middle?
Say it again?
Isn't I in the middle, so can't you just say that it's, we know the value of n, right? How many there are, but we.
Right. But we got to be able to add each one up, right? This is, when I do this sigma, you can't, that's a really powerful thing. What that's doing is it's saying we're going to add up this whole expression for each of these individual values of I.
I thought I was in the middle. How do you know?
What?
Is that the same I as the I in the
Different eyes.
Is the I in what?
Is the I in the
Yeah, absolutely. That I is this guy.
Yeah, but
It's just,
I doesn't equal 1.
no, I equals all values from 1 to n. I is what we call the index variable. So it's,
So you should use a different variable there.
No, but isn't that I in the middle?
this is an I, that's a 1.
No.
No, go back to the
The sigma.
sigma.
So under the sigma, that I is the exact same I.
Yeah,
No,
absolutely.
but I doesn't equal 1.
Hey, why does it?
No, 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 but that's how I,
there have a curly.
right, but that's,
Same.
let me remind you about sigma notation. Maybe, okay, I see what the problem is. Here it is. Little quick review. If I want to do this, if I want to say 1 plus 2 plus 3 plus 10, how do I say that with
Sigma
sigma
I
notation? That's the sum of
Alright, equals 10.
I as I goes from 1 to 10.
Ah.
Okay? How would I do this? How would I do, how about if I have the sum of 1 squared plus 2 plus 2 squared plus 2 plus 1,000 squared plus 2.
So sigma I, whatever that, or
Of what? What does each one of those individual terms look like in terms of
I
I?
squared plus 2.
Ah, I squared plus 2, right? Because this is the one we would get right here for I equals 1, I equals 2, I equals 1,000. Where is the I showing up?
So it's I squared plus 2.
Right there, right?
So the index I and the
Uh,
I
the
in the
index
graph,
is
they're
the plus
different I's.
Oh, you mean?
No, they're the same.
No, but the one in the graph, did you say that was like the middle?
Well,
Those are really
I-
bad
there-
there.
Okay, I showed it in the middle as not to, let me hold that thought for just 1 second. Would everybody agree this is the sum of I squared plus 2? Okay. Okay, now, okay, so here's the question Yen is posing. Somebody answer this. I'm getting tired of talking. Somebody else answer this. This I right here, suggestion is that's not the same as what I'm talking about with the sigma. Okay, because this I is in the middle. Okay, why did I draw that in the middle? It doesn't have to be. I represents one and every one of those individual rectangles. Why did I draw it in the middle? Why didn't I draw it as the first or the last? I could have.
Doesn't matter.
I could have, but then it's not as generic looking, is it? If I put it out here, notice I've got this dot, 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 and this dot, dot, dot. There's no specificity with the location of that thing. It's just where it is. It's just one of any random locations of the rectangles. But I is the index variable. It accounts for each click or each step on the trip. I is 1, 2, 3, 4, etc., all the way to the end. So this just represents the concept of an index variable. Okay?
So I can go anywhere.
Yeah, I is just going to, incrementally, it's going to walk up from its initial value to its final value, right? Okay, so then what about, so here we have it. All we have to do is just add this thing up, right? That's all we have to do is add that up. Now, we could do this manually. We could say when I is 1, what does that equal? Plus when I is 2, what does that equal? Plus, we don't want to do that, though. So your graphing calculators, now this is, I'll show you how to do this trick on your graphing calculators. Against all better judgment, I'm going to show you right now
Hey, I
instead
just want to let
of...
you know, I just downloaded an excellent calculator on my iPod. Which
Nice.
has multiple conversions, multiple laws of physics and mathematics.
I've got one too.
And I purchased it
Very
for
good.
$2.99.
Yep.
It was a great purchase.
Yep.
You should see this app though. It does like a lot.
The only game we're looking at, we ever play Osmos. Oh, yeah.
Is it worth it?
Oh, it's worth $5 for that.
Jailbroke your iPod, man. Just free.
It's alright.
I got the
it pretty
jailbroken.
quick, but it was awesome.
That's in jail.
Osmos.
Okay, so here it is. Everybody get out your calculators. I'm going to show you, I'll give you the goods on how you can add these things up with your calculators.
Mine's been broken for a couple months.
Just go ahead and go.
What's that?
You go. I think I know the
You know how to do it?
I think so.
Okay. Okay, Smarty Pants, how do you do it?
Everyone listen to Lane.
I don't know where how you find it, but it's like the list things and
Okay, yeah, that's, the old way to do it is you do sum of sequence, but I think on the new operating system, the first time I've done it since I've got the new operating system, but I think if I go math and I go number, I
Do
bet,
you have enough money on here for?
you go. How coding.
I'm going to see if they have a sigma sign on here.
Okay, my Inspire has a sigma, you just punch it in.
Yeah, the Inspire would, yeah. I don't, maybe this one.
There's summation. Yeah, there's summations on the math.
Oh, there it is right there. Yep, under math. Okay, summation, that's what we want. So we're going to do, oh, look at that. Man, that's awesome.
Whoa.
How about that? That's all new. It never used to be
We had
there.
that last year.
No, it did not.
And Mr. Jones' class.
Not like that, it
I used
didn't.
to use that.
Serious?
Yeah.
Well, he had the calculator last year.
Oh, okay.
I'm a little
Okay.
more advanced than you.
Evidently. Okay, so what goes where? We're just literally going to put all this stuff in.
That's cool.
Okay. Okay, so we want to, now we can't choose I as a variable, so we're going to choose X. That's the only front screen variable. How do you choose I? I guess if you choose an I, maybe, if you just go alpha I.
Also, there's a, but I think
Serious?
that's really don't forget these. That's different. I think that's
You know what?
Oh, that's, okay. Now that's, okay, that might be a mistake, because that's going to choose the imaginary unit I think.
No, but why does it on the X button, why does it have all those different choices?
Well, because you can change the mode to be in terms of parametric equations, or you can write it in terms of, you can use an angle to do trig stuff. It's never ever worth doing though. What you just do instead is just let X be the variable that you know, instead of theta, just call it X, big deal.
Doesn't X have values?
No, it'll store values, but within the calculator, you mean like when I say store as X?
So if I were just put variable one or put
Yeah, like
click X.
Yeah, that's the same thing.
Yeah, then there's going to be some random number stored in there, but we don't care about that.
That one affects
No, it won't. It won't. Because when the calculator executes this function, it's going to store the right stuff. It's going to store things as X itself. Okay, so X goes from 1 to, if I go up to 100, and then I have to write this expression in terms of X's instead of I's. Big deal. So in parentheses, I've got 4 minus X squared times the quantity 1 divided by 50 squared. Close that bracket, right? Times 1/50th. Should I just say divided by 50? Okay? Agreed? Did I get it in there? Yeah. Okay, so
Equality.
it's thinking 5.2932. Now, what did Ethan's guess was 5.25?
So he's wrong.
This is a little better guess.
Yeah, wrong.
It's a little better guess.
I did not get that.
Is your calculator in the right mode?
It'd be easy to probably make a mistake putting all this stuff in.
I didn't get that.
If you're,
I didn't get that because I have my
My
calculator.
calculator doesn't have backwards.
Oh, okay, so you really didn't get that.
Yeah.
Okay, do we want to know what the actual answer is?
Sure.
Here's how you can find the actual answer. Now I'm not gonna tell you why. We can go math.
Didn't get it.
If we go down to right there, number 9, finite integral. Now look at that sign.
Ooh, hot damn.
Whoa, that's the antiderivative sign. We're gonna go from x equals 0
That just looks cool.
yeah, hey, I just want to hit this button to see it.
to x equals 2, and we're adding up the area under the curve. 4 minus x squared. And the variable of integration is x. Okay, and the answer is 5 1/3. It's the actual exact answer.
Where's the 100 go?
We didn't need it for this.
Where's the
This is in about a section and a half. We'll learn that trick.
Where's the antiderivative sign on the calculator?
Math number 9. Okay.
Yo, then.
Math 9.
Okay. So far so good.
So good.
Okay, that was pretty nice because we were able to choose the value of n. We were able to set the value of n however we wanted to. Now on our calculator,
You wanted to.
okay, here's the challenge. See if we can figure this out. This should be pretty cool if we can do this. Let's see if we can set this expression up in terms of n's. So let's go back up to here. Clear that out. Oops.
Uh-oh.
That's it. Oh, I didn't want to do that. I want to do that.
The little crane that could.
Clear.
No, it's the little train.
You want something clear in a second.
I want to try to roll it back, but I think I just got rid of it. Oh well.
No, second, wait.
Okay.
What's it here?
Oh, maybe I can get back.
Jennings.
I always have to redo this whole thing. Yeah, never mind.
I'm almost stupid jaws.
Okay. So could we write this now? Let's see here. Here's the challenge. Can we write this where we don't specify n?
I did this. That's really good.
Anybody know a way to do that? Matt, you know a way to do that? Put that on.
Alright, I know how to do that.
One more time.
Because that would be really cool if we could do that. Can we put this in so I know how maybe we can do it. Oh, this would be pretty cool. Okay, let's try this. Okay, let's try this. Oh, okay, this is gonna be good. Okay, try this. Here's what we're gonna do. Here's the theory. This might just totally fall apart. But here's the theory. The theory is
Oh.
Yeah, what is this?
Sure, just throw it away.
oh wait, never mind. Okay, here's what I'm going to see if we can do. Can we do this? Okay, let's see if we can do that. So I think what this is going to do is this is going to graph. I don't know, this might explode the calculator, but let's try it. I think that if we go to a table and we let x, if we look at different values of x, we ought to be able to.
No, the calculator actually did this for us.
Okay. If this works, this will be great.
I think so.
Okay, so you got now. I'm gonna probably mess this up, so you gotta follow me. Make sure I don't make a mistake.
You're the teacher. You shouldn't make a mistake.
Oh, I'm likely to make a mistake.
I don't.
Okay.
Whoa! Watch it.
What number was that? 0?
Nine.
0. Okay. So now we got to put in something other than x there. Let's put in like
T.
let's put in 8.
How come we include
Because x is going to be the upper limit.
Oh, okay.
Okay. This is just the index variable. It's going to go from 1
You
to
have something stored for A, will that change it?
x. Oh, this will be
the
slow.
whole time. Totally broke through my window last night.
Did you have something stored for A, will that change it?
What's that?
Did you have something stored for A, will that change it?
No, it'll store. It's going to let a run
Bastard.
from 1 to x. Okay.
You heard me.
Okay. So what goes in there? Then we've got 4 minus a squared times well, because I'm using x to be the upper limit, so we're going to let x vary.
Shooting yourself. Oh.
Okay. Okay.
See you next week.
Doesn't even go.
Okay, let's see here. How's it going to work?
Champagne does better than that.
Okay, now if I go table. Oh, check it out. It did it.
Wow. Now that is the type of match.
It's not doing the right thing.
Jesus.
Yeah. Huh.